A flash of light in the sky once decided the fate of an empire. Throughout history, celestial events have not just been spectacles, they have been active players in the human story. This journey through 28 astronomical events will reveal how the cosmos has repeatedly rewritten our history, shaping everything from religions to scientific revolutions. You will discover the true scale of our connection to the universe. How did a comet convince an army to surrender? What star signified the birth of a new era? By the end, you will see the past not as a series of isolated events on Earth, but as a dialogue with the heavens. What single event in the sky do you think could change our world tomorrow? In the year 1054, a new star erupted into being where none had been seen before. For 23 days, it burned so fiercely it was visible even at noon, a brilliant pinprick of light outshining every planet in the sky. Cultures around the world watched in awe. Chinese court astronomers called it a guest star, meticulously documenting its position. Japanese stargazers saw a celestial omen. In the American Southwest, ancestral Puebloan artists may have captured its likeness on a canyon wall, a handprint beside a star and a crescent moon. This was not a quiet event. It was a stellar explosion of unimaginable power, the death throes of a massive star that we now know created the beautiful Crab Nebula. But its true impact was not just in the light show. It directly challenged one of the most deeply held beliefs of the ancient world, the idea that the heavens were perfect and unchanging. For philosophers like Aristotle, the realm beyond the moon was a place of eternal, divine order, immune to the decay and chaos of Earth. This new star, this violent change in the pristine night sky, was an impossibility. Its very existence was a crack in the foundation of classical cosmology. It provided the first undeniable proof that the cosmos was alive, dynamic, and capable of radical transformation. The remnant of that star, a rapidly spinning neutron star at the heart of the Crab Nebula, still pulses with energy today, a cosmic beacon from an event that shattered old paradigms. The supernova of 1054 did more than just light up the sky. It planted a crucial seed, the idea that the universe could be studied not through dogma, but through observation. It was a celestial push that would, centuries later, help fuel the scientific revolution. This profound shift from a static sky to an evolving one sets the stage for our next encounter, where the heavens did not just challenge human belief, but appeared to fulfill a divine prophecy. Centuries after a star challenged the foundations of philosophy, another celestial light appeared with a very different purpose. It guided travelers to a humble birthplace, an event that would weave a cosmic thread directly into the fabric of Western culture. The Star of Bethlehem, as described in the Gospel of Matthew, led the Magi from the east to the infant Jesus. For 2,000 years, this single verse has inspired one of history's most captivating astronomical detective stories. Was it a miraculous sign, or could it be explained by the predictable clockwork of the heavens? Scholars and astronomers have proposed compelling theories. One of the most famous suggests a spectacular planetary conjunction. Around the year 7 BC, Jupiter and Saturn, the two largest planets in our sky, drew so close together in the constellation Pisces that they would have appeared as a single, brilliant point of light. This was not a one-night event. Over several months, the planets performed a celestial dance, moving closer, then apart, then closer again in what is known as a triple conjunction. To ancient astrologers, the symbolism would have been profound. Jupiter was often associated with kingship, Saturn with the Jews, and Pisces with the lands of the West. A kingly planet meeting the Jewish planet in the western sky could easily have been interpreted as a portent of a Messiah's birth in Judea. Another possibility points to a different object entirely. Chinese and Korean star records note the appearance of a bright comet in the year 5 BC, which remained visible for more than 70 days. A comet with its long, sweeping tail would have been a dramatic and unmistakable herald in the night sky. Whether it was a planetary meeting, a comet, or a singular supernova, the impact of this celestial story is undeniable. It placed a star at the center of the nativity narrative, forever linking the divine with the cosmos. This single event influenced countless works of art, shaped theological thought for centuries, and even affected the very calendar system used by much of the world today. The relentless human quest to identify this star, to pin a natural explanation onto a foundational story, itself drove forward the field of historical astronomy. It showed how a moment of celestial wonder could define an entire era. But the sky does not only promise hope and new beginnings. Sometimes it delivers a message of absolute and terrifying finality, a warning that even the mightiest empires are not immune to the judgments of the cosmos. That same sky which promised a divine birth could also deliver a verdict of doom. Centuries before the Star of Bethlehem, the sun performed a terrifying vanishing act over the Assyrian Empire. In the year 763 BC, in the midst of a sweltering day, the light began to fail. The sky turned a sickly bronze, the air grew cold, and day was transformed into an eerie, premature night. For the people of Nineveh, the capital of the most powerful empire on earth, this was not a scientific curiosity. It was a cataclysm. Assyrian scribes, with meticulous precision, recorded the event on clay tablets, noting the month and the day the sun god Shamash turned his face away. In their worldview, the king was the direct link to the gods, and the cosmos was a mirror of divine will. A solar eclipse was the ultimate omen, a clear sign that the gods had withdrawn their favor from the ruler. It was interpreted as a divine abandonment of King Ashur-dan III, whose reign was already plagued by civil unrest and revolts. The eclipse did not physically destroy the city, but it shattered something far more critical, the unshakable belief in the king's legitimacy. It fueled internal dissent and created a political vacuum of doubt that the empire never fully recovered from. While Nineveh would not fall for another few decades, this celestial event was a crucial crack in its foundation, a moment when the heavens were seen to actively conspire against a throne. This profound fear of the sky's caprice is what drove the very first astronomers to power. In Mesopotamia, priests began to notice patterns, cycles in the movements of the sun and moon that allowed them to predict future eclipses. This knowledge became a source of immense political control. A priest who could predict the sun's return could calm a panicked population and affirm the king's renewed divine connection. The ability to foresee such events transformed astronomy from mere observation into a tool of statecraft, a way to harness the terror of the cosmos. The eclipse that helped doom an empire ultimately set humanity on a path toward truly understanding the clockwork of the solar system. From an omen that foretold the fall of a great city, we now journey to a celestial event that did the opposite, guiding desperate sailors to the safety of an unknown shore. A predictable streak of light in the heavens became the ultimate arbiter of destiny. In the spring of 1066, a brilliant comet with a long, fiery tail unfurled across the European sky. Its arrival was meticulously recorded in the stars of the Bayeux Tapestry, a sprawling, embroidered chronicle that tells the story of the Norman conquest of England. There, the comet hangs ominously in the sky, a celestial spectator to a pivotal human drama. For the two armies preparing for war, this single object held two completely opposing meanings. To William, Duke of Normandy, and his invading forces, the comet was a divine endorsement, a shining signal from God that his claim to the English throne was just and his victory assured. For the English King Harold and his men watching that same star with dread, it was a terrible omen, a sign of God's wrath and the impending downfall of their king. This was Halley's comet, a regular visitor to our inner solar system, but in that year its appearance was anything but routine. It was a psychological weapon of immense power. When the armies finally clashed at the Battle of Hastings, the Norman interpretation of the celestial sign seemed to be proven right. King Harold fell, and William the Conqueror seized the throne. The aftermath of that single day reshaped England forever, transforming its language, its legal system, and its very culture, weaving Norman French into Old English to create the foundation of the language we speak today. The comet itself was a natural phenomenon, a ball of ice and rock following the same gravitational path it has traveled for millennia. Yet its human impact was entirely manufactured, a story written in the stars by the people who saw it. The legacy of 1066 is a stark lesson in the power of perception. It demonstrates that the true force of a celestial event lies not in its physical properties, but in the meaning we choose to assign it. We project our deepest fears and our grandest ambitions onto the blank canvas of the night sky, and sometimes that projection becomes a self-fulfilling prophecy. This human tendency to seek meaning in the stars would next drive explorers to use the heavens not as an omen, but as a literal map, leading them to the edge of the known world and beyond. 4 centuries after the Crab Nebula's light faded, another star detonated in the sky, and this time a man was watching with a revolutionary mind. Tycho Brahe, the eccentric Danish nobleman with a metal nose and a passion for precision, looked up in November 1572 and saw the impossible. In the constellation Cassiopeia, a star blazed where no star had been charted, outshining Jupiter itself. This was not a distant, flickering point. It was a brilliant, undeniable fact that refused to be ignored. Tycho did what no one had ever done with such rigor for a new star. He measured its position night after night, using his own custom-built giant sextants and quadrants, instruments of unprecedented accuracy. He proved the object showed no parallax, meaning it was not a nearby atmospheric phenomenon, but resided firmly in the realm of the fixed stars, the very domain Aristotle had declared eternally perfect and unchanging. The supernova of 1572 was a direct contradiction written in fire across the sky. It was empirical evidence that could not be argued away. Tycho's book De Stella Nova presented his data to the world, and it became a manifesto for a new way of thinking. The cosmos was not a static, perfect crystal sphere. It was a place of birth, death, and violent transformation. This single event shattered the intellectual chains of 2,000 years, empowering a generation of thinkers to trust their eyes over ancient texts. The data Tycho collected, especially from the supernova and his later observations of Mars, provided the crucial raw material for his assistant, Johannes Kepler, to deduce the elliptical orbits of planets, finally breaking with the perfect circles of Greek astronomy and paving the way for Newton's laws of gravity. This stellar explosion was more than a light show. It was the moment astronomy grew up, shifting from philosophy to physics. It gave scientists the courage to challenge authority with observation, a confidence that would soon be tested by an even more profound cosmic disruption, one that would question the very order of the solar system. The predictable clockwork of the heavens would soon be used to test an idea so radical it seemed to defy common sense. In May 1919, 2 teams of British astronomers led by Sir Arthur Eddington traveled to opposite ends of the Earth, one to the island of Principe off the coast of Africa, and the other to Sobral in Brazil. Their mission was audacious: to use the brief, perfect darkness of a total solar eclipse to prove or disprove a German physicist's theory, conceived in the midst of a world war. Albert Einstein's general theory of relativity proposed a universe where gravity was not a mysterious force, but a warp in the very fabric of space and time. A massive object like our Sun would cause this fabric to curve, and light from distant stars traveling along this curvature would appear to bend. The only time you can see those stars near the Sun to measure this effect is when the Moon perfectly blocks the Sun's blinding face. On the day of the eclipse, clouds threatened to ruin everything for Eddington on Principe, but in the final moments of totality, the sky cleared just enough. His team took photograph after photograph of the Hyade star cluster positioned right behind the Sun's obscured disk. When they developed the plates and compared the stars' positions to their known locations at night, the results were undeniable. The starlight had been deflected by almost exactly the amount Einstein had predicted. The Sun's gravity had acted as a cosmic lens. This was not merely a new fact, it was a complete overhaul of reality. Matter told space how to curve, and curved space told matter how to move. The news that a British expedition had confirmed a German theory just after the war ended sent shockwaves through the world, transforming Einstein overnight into an international celebrity and a symbol of science transcending conflict. The eclipse of 1919 did more than validate a brilliant mind. It flung open the door to modern cosmology. It gave us the tools to conceptualize black holes, the expanding universe, and the bending of light from galaxies billions of light years away. A few minutes of celestial alignment, carefully observed, forever changed our place in the cosmos, proving we live not in a rigid, predictable void, but within a dynamic, flexible stage where space and time themselves are players. This new understanding of gravity as a geometric force would soon be used to explain an even grander motion, the subtle wobble of a planet that refused to follow the rules. Stranded on the shores of Jamaica in the year 1504, Christopher Columbus was a man on the brink of disaster. His ships were rotting, his crew was mutinous, and the local Arawak people, who had initially provided food, were growing weary of the endless demands from these strange visitors. The situation was desperate, and a failed colony meant certain death by starvation. But Columbus held a secret weapon, not a sword or a cannon, but a book. He possessed an almanac, a detailed forecast of celestial events compiled by a German astronomer, and within its pages he found his salvation, a prediction for a total lunar eclipse on the night of February 29th. He saw not a scientific phenomenon, but a stage for a terrifying performance. He requested a meeting with the Arawak chief and delivered an ultimatum. He claimed his Christian God was deeply angered by their lack of support, and as a sign of his divine wrath, he would make the full moon vanish from the sky, bathing it in a blood-red glow. As the appointed hour arrived, the Earth's shadow began its slow crawl across the lunar face. The moon, a constant companion in their night sky, was indeed consumed by darkness, just as the foreigner had promised. Panic spread through the Arawak community. Convinced they had provoked a powerful deity, they immediately capitulated, pleading with Columbus to restore the moon and promising a steady supply of provisions. He, of course, graciously agreed, retreating to his quarters to time the eclipse with his hourglass before emerging to announce his god was appeased as the moon slowly returned to its normal brilliance. This was not a miracle, it was a masterful act of psychological manipulation. Columbus weaponized knowledge using a predictable alignment of the sun, earth, and moon to secure his own survival. This event underscores a dark chapter in the age of exploration. where astronomical understanding became a tool of coercion and control, directly impacting the dynamics of early European colonization. It was a deception that reinforced a power imbalance, turning celestial mechanics into a life-saving lie. This cynical use of the heavens as an instrument of fear stands in stark contrast to an event just over a century later, when a celestial visitor arrived not to manipulate, but to inspire a revolution in human thought. A comet with a tail spanning half the sky dominated the heavens for more than 260 days. The Great Comet of 1811 was not a fleeting visitor. It was a lingering, brilliant spectacle that captivated and unsettled the entire world. For nearly 9 months, its ethereal glow was a constant fixture, a celestial mystery that sparked both wonder and a deep, primal anxiety. And then the Earth itself seemed to respond. Just a few years later, in 1815, the colossal eruption of Mount Tambora in the Dutch East Indies hurled an immense veil of volcanic ash into the stratosphere. This was followed by the cataclysm of 1816, a year so cold and bleak it earned the name the year without a summer. Global temperatures plummeted. Frost blackened crops in July, snow fell in New England in June, and relentless rain drowned European harvests. The result was a worldwide catastrophe, widespread famine, food riots, and a desperate mass migration from the colder climates. In the midst of this global misery, the human mind instinctively searched for a cause, a pattern to explain the suffering. The memory of that magnificent, long-tailed comet was still fresh, and the connection seemed obvious. People from Europe to America linked the celestial event directly to the earthly disaster, believing the comet had somehow poisoned the air or disrupted the natural order of the world. This was a classic case of post hoc reasoning, where one event is mistaken for the cause of another simply because it happened first. Yet from this period of darkness emerged a surprising cultural dawn. Trapped indoors by the incessant cold and rain during a holiday at Lake Geneva, a group of friends including Mary Shelley and Lord Byron turned to storytelling to pass the time. The gloomy, storm-racked atmosphere, a direct consequence of the volcanic winter, provided the perfect inspiration for a tale of unnatural creation. Mary Shelley's Frankenstein was born from that summer of despair, a timeless story that questioned the very limits of science and humanity. The Great Comet of 1811 demonstrates a profound and enduring human trait, our need to weave narratives, to connect the dots between the heavens and our lives, especially when confronted with the unexplainable. It was not the comet that caused the frost or the famine, but the perception of a connection that shaped history, fueling both fear and a lasting artistic legacy. While humanity was learning to separate celestial coincidence from terrestrial cause, another mystery was brewing in the solar system, a persistent wobble in the orbit of a known planet that would point the way to an unseen world. A faint, slow-moving smudge of light drifted through the constellation of Gemini. On the night of March 13, 1781, German-born musician and amateur astronomer William Herschel was conducting a systematic survey of the heavens from his garden in Bath, England. With a telescope of his own masterful construction, he noted this curious object that seemed just a little too large and too fuzzy to be an ordinary star. He initially assumed he had found a comet, a common enough discovery for a dedicated sky watcher, but as he tracked its motion night after night, its path was wrong. It moved too slowly and followed a nearly circular orbit, unlike the elongated, sweeping trajectory of a comet. The realization dawned that this was no icy visitor from the outer solar system. He had found something far more monumental, a new primary planet, a world orbiting our sun beyond the ringed giant Saturn. He named it Georgium Sidus, the Georgian star, in honor of King George III, though the name Uranus from the ancient Greek god of the sky would eventually prevail. The announcement sent shockwaves through the scientific community. For thousands of years since the dawn of astronomy itself, the solar system was a settled fact. There were 6 planets plus Earth, a tidy family whose boundaries were set by Saturn. This was the model taught in universities, the foundation of celestial mechanics. Herschel's discovery shattered that ancient consensus in an instant. The known size of our planetary system doubled overnight. Suddenly, the solar system was not a small, well-lit room, but a vast hall with at least one more, previously hidden door. This single observation ignited a fever for planetary discovery. It proved that the tools of science could reveal worlds hidden in plain sight, and it transformed astronomy from a study of the known into a hunt for the unknown. The public imagination was set ablaze. Herschel became a celebrity, and a newfound enthusiasm for the stars swept across Europe and America. More profoundly, the discovery of Uranus forced a fundamental shift in perspective. Humanity was not at the center of a small, familiar system. We were inhabitants of a much larger, more dynamic, and far more mysterious cosmic neighborhood. This expansion of our horizons, however, came with a puzzle. Uranus itself soon began to stray from its predicted path, as if tugged by an unseen hand, a gravitational mystery that would itself point the way to yet another world waiting in the dark. The new planet Uranus, a triumph of observation, soon became an astronomical embarrassment. It stubbornly refused to follow its predicted path, drifting slightly off course in a way that Newton's laws of gravity could not explain. Was the great Newton wrong, or was something else, something massive and unseen, pulling on the distant world? This celestial tug of war became the greatest puzzle in 19th century science. 2 brilliant mathematicians, a Frenchman named Urbain Le Verrier and a Briton named John Couch Adams, took up the challenge independently. They never met, they never collaborated, but they both turned to the same powerful tool, the language of mathematics. For months they wrestled with complex equations, using only pen, paper, and the power of their minds. They treated the solar system as a grand cosmic clockwork, and the wobble in Uranus' orbit as a missing gear. By calculating the precise gravitational pull needed to cause that wobble, they could predict the location of the hidden culprit. Le Verrier, with unwavering confidence, finally sent his coordinates to the Berlin Observatory. There, on the night of September 23, 1846, astronomer Johann Gottfried Galle pointed his telescope to the exact spot in the sky Le Verrier had specified. And within 1 degree of that predicted position, he found it, a faint blue-green disk, not a star, but a new world. They named it Neptune. This was not a discovery by chance. It was a discovery by thought. A planet was found at the tip of a pen before it was ever seen through a lens. The impact was seismic. It was the ultimate validation of Isaac Newton's universal law of gravitation, proving that the same force that made an apple fall on Earth also governed the motion of planets billions of miles away. The universe was not just orderly, it was knowable. Human reason, armed with mathematics, could reach into the void and pull out a world. This event transformed astronomy forever. It was no longer just about cataloging what was visible. It was about predicting what must be there. It cemented the scientific method as our most powerful tool for uncovering cosmic truths, empowering humanity with the profound belief that the secrets of the universe could be decoded. Yet this hard-won confidence in a predictable, clockwork solar system was about to be shattered by an event of sheer, unpredictable violence, a collision from the depths of space that would remind everyone of the chaos lurking in our cosmic neighborhood. The cosmic clockwork revealed by Neptune's discovery offered an illusion of perfect order, a solar system running on predictable, mathematical rails. That illusion was shattered on a June morning in 1908. over the remote Siberian wilderness of Tunguska. A blinding fireball brighter than the sun tore across the sky, culminating in a cataclysm of unimaginable force. The explosion, equivalent to a multi-megaton bomb, flattened 80 million trees across 2,000 square kilometers, radiating out from the epicenter in a vast butterfly pattern of destruction. The shockwave was so immense it circled the globe twice, and for nights afterward, skies across Europe and Asia glowed so brightly that people could read newspapers outdoors at midnight. When scientific expeditions finally reached the inaccessible site years later, they found a scene of utter devastation but no crater. The culprit was not a direct impact, but an airburst, a stony asteroid or comet fragment roughly 60 meters across that detonated in the atmosphere several miles above the ground, releasing all its colossal kinetic energy in a single, devastating blast. Had this event occurred just a few hours later in Earth's rotation, it could have vaporized a major European city, instantly rewriting the political and social landscape of the 20th century. The Tunguska event served as a stark and sobering wake-up call. It proved that cosmic collisions were not just theoretical threats from the deep past, but active, ongoing dangers. A relatively small object, a mere speck in the grand scheme of the solar system, could unleash the destructive power of 1,000 Hiroshima bombs. This single event fundamentally reshaped scientific priorities, transforming the study of near-Earth objects from a niche curiosity into a critical field of planetary defense. It forced humanity to look up with a new sense of vulnerability, acknowledging that our world exists within a cosmic shooting gallery. This demonstration of raw, localized power from a single small object makes the sheer scale of our next encounter almost impossible to grasp, for it involves not a lone asteroid, but the entire structure of our galaxy revealing itself. From the terrifying local impact of a single asteroid, we now shift our gaze to a discovery that redefined the entire cosmos. Perched high above Los Angeles at the Mount Wilson Observatory, Edwin Hubble was staring into the deepest reaches of space. He was not just looking at galaxies, he was listening to the story their light told. By meticulously analyzing the faint glow from these distant island universes, Hubble noticed something peculiar. The light from nearly all of them was shifted toward the red end of the spectrum. This redshift was a cosmic echo, a Doppler effect on a universal scale. Just as the pitch of a siren drops as an ambulance speeds away from you, the light from these galaxies was stretched as they raced away from our own. The staggering implication was that the universe itself was not static. It was expanding, carrying these galaxies along with it like raisins in a rising loaf of bread. This single observation, confirmed in the late 1920s, shattered the prevailing model of an eternal, unchanging cosmos. The universe was not simply there, it was actively becoming. This discovery was the first direct observational evidence for what would become the Big Bang Theory, the idea that the entire universe exploded from an infinitely hot, dense initial state. We were no longer inhabitants of a stable, eternal stage, but passengers on a cosmic journey that had a definite, violent beginning. The philosophical shockwaves were profound. If the universe had a beginning, did it also have an end? What existed before that moment of creation? Hubble's work did not just add a new fact to astronomy, it recontextualized everything. It placed humanity inside a dynamic, evolving story, a grand narrative with a prologue written 14 billion years ago. This understanding of a violent, expanding beginning sets the stage for observing the violent deaths that continue to shape it. Deep in space, a new kind of violence was accidentally discovered. During the late 1960s, a fleet of American Vela satellites silently orbited the Earth, their sensitive instruments tasked with a singular, secret mission: to monitor the heavens for the telltale gamma-ray signature of clandestine nuclear weapons tests. They were built for espionage, not astronomy, but they began picking up something entirely unexpected: brief, intense flashes of gamma rays that did not come from Earth or our Sun. They originated from random points across the entire sky, appearing without warning and vanishing in seconds. These were not the gentle flickers of distant stars. They were titanic eruptions, the most powerful explosions the universe has produced since its own fiery birth in the Big Bang. The discovery of gamma-ray bursts, or GRBS, was initially kept classified, a cosmic secret. When the data was finally declassified years later, it presented astronomers with a profound mystery. What natural phenomenon could possibly generate, in a matter of seconds, more energy than our Sun will emit over its entire 10 billion-year lifetime? The answer was as terrifying as it was magnificent. We now believe these flashes mark the birth cries of newborn black holes, either from the catastrophic collapse of a massive, rapidly spinning star into a supernova, or from the violent merger of two ultra-dense neutron stars. These are events so powerful they warp the very fabric of space-time, sending ripples of gravity across the cosmos and forging heavy elements like gold and platinum in their furnaces. The study of these distant cataclysms has forced us to rewrite the book on stellar evolution and revealed a universe far more dynamic and violent than we ever imagined. Witnessing the death throes of stars from the safety of billions of light years away, however, prepares us to examine a stellar death that hit much closer to home, one whose fallout we can still touch today. A morning commute in the Russian city of Chelyabinsk was shattered by a light brighter than the sun. On February 15, 2013, a house-sized asteroid, traveling at nearly 40,000 miles per hour, tore through the atmosphere. It was a superbolide, an explosion of fire and force that for 30 seconds painted the sky with a terrifying, evolving trail of white smoke and orange fire. The spectacle was only the beginning. Minutes later, the shockwave arrived, a thunderous wall of compressed air that shattered windows across the city, sending thousands to hospitals with cuts from flying glass. The event injured over 1,000 people, not from falling rock, but from the sheer atmospheric violence of its passage. This was the Chelyabinsk Meteor, the largest object to collide with Earth since Tunguska over a century before. But this time, the event was not a mystery confined to a remote wilderness. It was documented in real time by an entire city's worth of dashboard cameras, providing a staggering, multi-angle dataset that transformed our understanding of such impacts. Scientists could now analyze the exact trajectory, the breakup sequence, and the energy release with a precision that was previously unimaginable. The videos did more than provide data. They delivered a visceral, undeniable truth directly into the public consciousness. Here was a cosmic impact, not in a history book or a sci-fi film, but on the daily news, reminding everyone that the threat from space is not a theoretical future problem, but a present and ongoing reality. The global response was immediate and coordinated. Governments worldwide significantly boosted funding for planetary defense initiatives, leading to new telescopes and enhanced international cooperation dedicated to finding and tracking potentially hazardous near-Earth objects. Chelyabinsk was a stark, modern-day drill, a tangible encounter with a rock from space that made the cosmic shooting gallery feel terrifyingly personal. This direct physical evidence of our vulnerability stands in profound contrast to the next discovery, an object so strange it was not found by a telescope's eye, but through the pure, predictive power of theoretical insight. Two young radio astronomers at Bell Labs were trying to eliminate a persistent, maddening hiss. Arno Penzias and Robert Wilson, using a massive horn-shaped antenna in New Jersey, were plagued by a faint, uniform static that came from every direction in the sky. They scrubbed the entire apparatus, even evicting a pair of pigeons and meticulously cleaning up their droppings, convinced the noise was a mundane terrestrial interference. But the hiss remained, a constant, omnipresent whisper that defied all their efforts to erase it. This irritating background noise was not a technical flaw. It was the oldest light in the universe. They had accidentally stumbled upon the cosmic microwave background radiation, the cooled and stretched remnant of the universe's fiery birth. This was the afterglow of the Big Bang itself, a fossil imprint from a time nearly 14 billion years ago when the entire cosmos was a searing, opaque plasma. The discovery was the final, definitive piece of evidence that settled the great cosmological debate of the 20th century, the rival steady-state model, which proposed a universe with no beginning or end, eternally creating new matter to maintain its density, could not explain this pervasive, cool glow. The CBM was the smoking gun, the cooled embers of the primordial fireball, and it confirmed that our universe did indeed have a dramatic, hot beginning. This relic radiation is not just a static picture, it is a data-rich cosmic parchment. By mapping its incredibly subtle temperature variations, tiny anisotropies, just a few millionths of a degree, cosmologists have been able to read the story of the infant universe. These minute fluctuations are the seeds of all future structure, the gravitational blueprints for the first stars, galaxies, and clusters. The CBM allows us to measure the age, composition, and even the geometry of the cosmos with stunning precision, revealing a universe made of dark energy, dark matter, and a small fraction of ordinary atoms. This accidental discovery, for which Penzias and Wilson won the Nobel Prize, cemented our cosmic origin story. It gave us a tangible connection to the moment of creation, a whisper from the dawn of time that we could suddenly hear. This profound ability to look back required a new kind of eye, one that could see not just light but the very fabric of the universe. A flawless new eye was opening to the universe. In April 1990, the Space Shuttle Discovery carried the Hubble Space Telescope into orbit, a masterpiece of engineering designed to see the cosmos with a clarity never before possible. But the initial euphoria quickly curdled into despair. The first images it sent back were blurry, a heartbreaking defect traced to a microscopic error in the shape of its primary mirror, a flaw smaller than a human hair that rendered the $2.5 billion observatory nearly blind. For 3 years, Hubble became a punchline, a symbol of costly failure. Then came one of the most daring rescue missions in history. In December 1993, astronauts aboard the Space Shuttle Endeavour captured the massive telescope and performed a series of complex spacewalks, installing a set of corrective lenses, a pair of cosmic spectacles. The world held its breath when the first new image appeared. It was a crystal-clear revelation. The fix was a perfect success. Hubble could finally see. Freed from the shimmering distortion of Earth's atmosphere, its vision was razor-sharp. It began to deliver a flood of data that would rewrite astronomy textbooks. It precisely measured the rate of the universe's expansion, pinning down the Hubble constant and helping to reveal the mysterious dark energy that drives cosmic acceleration. It confirmed the long-theorized existence of supermassive black holes, lurking like gravitational monsters at the hearts of galaxies. And by staring at a single, seemingly empty patch of sky for days, it created the Hubble Deep Field, an image that revealed thousands of galaxies in an area the size of a grain of sand held at arm's length, peering back to within 500 million years of the Big Bang itself. Beyond the raw science, Hubble transformed our cultural relationship with the cosmos. Its images became art, the pillars of creation, vast stellar nurseries of gas and dust, and the brilliant whirlpool of the Sombrero Galaxy were not just data points, they were breathtaking portraits that ignited public imagination and inspired a generation to look up. This orbiting observatory proved that to understand the universe, we sometimes have to leave our world behind. Its legacy of discovery set a new standard, paving the way for a new kind of telescope with a very different mission, one that would not just look at the stars but search for the planets circling them. For millennia, our solar system was the only example we had of planets at all. The idea of other worlds orbiting distant suns was a fantasy, a staple of science fiction with no basis in observed fact. That all changed in the autumn of 1992 with a faint, rhythmic signal from a cosmic corpse. Astronauts Alexander Wolskson and Dale Frail announced they had found not one, but 3 planets orbiting a pulsar, the rapidly spinning, super-dense remnant of a supernova explosion. This was a bizarre and hostile environment, a system born from stellar death. The discovery was monumental, proving that planets could form in the most unlikely of places, but it was still a curiosity. The real prize, the question that had haunted humanity for centuries, remained. Did planets orbit normal, sun-like stars? Just 3 years later, in 1995, the answer came from the Haute-Provence Observatory in France. Mitchell Mayer and Didier Queloz revealed the first planet ever found around a main sequence star like our own. They named it 51 Pegasi b. This world, however, was nothing like anything in our solar system. It was a gas giant as massive as Jupiter, but it orbited so close to its star that its year lasted a mere 4 Earth days. Its surface temperature would be scorching, over 1,000 degrees Celsius. This was a hot Jupiter, a type of planet that defied all existing theories of planetary formation, which stated giant planets could only form in the cold outer reaches of a stellar system. The discovery shattered the paradigm. Our solar system, with its rocky inner planets and gaseous outer giants, was not the template for the universe. It was simply one possible configuration among a staggering diversity of worlds. This revelation ignited the brand new field of exoplanetology, a scientific gold rush that has since catalogued thousands of alien planets. We now know that planets outnumber stars in our galaxy, with potentially billions of worlds waiting to be found. This abundance has forced a complete rewrite of planetary science. Theorists had to devise new models like planetary migration to explain how a gas giant could spiral inward so close to its star. The very definition of a habitable zone, the orbital region where liquid water could exist, had to be expanded and reconsidered. The primary goal of astronomy shifted profoundly. It was no longer a question of if other worlds existed, but what they were like. The new mission became characterization, analyzing the light that filters through an exoplanet's atmosphere during a transit to detect the chemical signatures of water vapor, methane, and even potential biosignatures. Every strange new world discovered, from super-Earths to mini-Neptunes, brings us closer to answering the most profound question of all. In a galaxy teeming with planets, how many have the specific, delicate conditions that allowed a world like ours to flourish? The ultimate verdict on the reign of the dinosaurs was delivered not from Earth, but from the depths of the solar system. 66 million years ago, a chunk of rock and metal perhaps 10 miles across, a fragment of cosmic debris left over from the planet's formation, found itself on a collision course with our world. It was not a slow, drifting approach, but a hypersonic impact, striking the shallow seas of what is now Mexico's Yucatan Peninsula. The asteroid released energy billions of times greater than the atomic bomb dropped on Hiroshima. The initial fireball incinerated everything within 1,000 miles. Then came the global shockwaves and mega tsunamis that scoured coastlines, but the real killer was what followed. The impact vaporized cubic miles of rock, hurling incandescent debris back into space. This material re-entered the atmosphere, superheating the air and triggering a global firestorm. Next, a dense, choking plume of dust and soot blotted out the sun for months, perhaps years, collapsing the food chain through a perpetual, freezing night. The final piece of the puzzle was found in a thin, global layer of clay. In the 1980s, scientists Lewis and Walter Alvarez discovered this geological marker was extraordinarily rich in the element iridium, a metal rare on Earth's surface but abundant in asteroids and comets. This iridium anomaly was the cosmic fingerprint, the undeniable evidence of a catastrophic impact. The final confirmation came when the massive, 110-mile-wide Chicxulub crater, buried under the Yucatan, was identified as the precise impact site. This solved paleontology's greatest whodunit, providing a single, catastrophic explanation for the sudden disappearance of 75% of all life on Earth, including the mighty dinosaurs. This event demonstrates with terrifying clarity that the course of evolution is not a slow, steady march, but a story punctuated by cosmic violence. The end of the dinosaurs was the opportunity for mammals. In the empty forests and plains of a devastated world, our small, shrew-like ancestors emerged from their burrows. With the dominant predators gone, they began to diversify, filling the vacant ecological niches and setting in motion the entire evolutionary lineage that would lead 66 million years later to us. The KT impact is the ultimate reminder that our very existence is a product of a chance encounter with a rock from space. It forces us to ask a profound question. If the cosmos can grant life an opportunity by clearing the board, could it also be the source of life's initial spark? The cold, dark clouds between the stars are far from empty. Tune a radio telescope to the right frequency, and you will hear a symphony of chemistry, a rich orchestra of complex organic molecules swirling in the void. These are not just simple gases. Astronomers have identified amino acids in meteorites that have fallen to Earth, and even detected the simplest amino acid, glycine, in the coma of a comet. These are the very building blocks of proteins, the fundamental components of life as we know it. This discovery fundamentally alters the question of our origins. We are no longer asking if life could have arisen solely from a primordial earthly soup, but if our entire planet was seeded with life's essential ingredients from space. This is the theory of panspermia in its rawest form, suggesting that asteroids and comets acted as cosmic delivery trucks, scattering the seeds of chemistry across the young Earth and countless other worlds. The profound implication is that the universe seems predisposed to creating the molecules necessary for biology. It appears to be a bio-friendly place, dramatically increasing the odds that what happened here could have happened elsewhere. If the raw materials for life are this common, scattered on asteroids and woven into the fabric of nebulae, then the potential for life beyond Earth seems not just possible but probable. The universe has provided the ingredients, but what lit the stove? What cosmic energy source could have taken these scattered molecules and assembled them into the first, fragile spark of life? One of the most familiar stars in our winter sky began to vanish. Betelgeuse, the brilliant red supergiant that forms the shoulder of the Orion constellation, underwent a dramatic and unsettling transformation in late 2019. Over a matter of weeks, its light dimmed by nearly 2/3, losing its place among the top 20 brightest stars. This was not a subtle flicker. It was a great dimming, visible to anyone who looked up, a celestial landmark fading before our very eyes. The event ignited a firestorm of speculation. Was this the final act? Was Betelgeuse, a star known to be in its death throes, about to explode in a supernova that would outshine the moon in our daytime sky? For a few thrilling months, the possibility felt real. The world watched, holding its collective breath for a cosmic spectacle unseen in our galaxy since the time of Kepler. The truth, when it was pieced together by astronomers using powerful telescopes, was almost as dramatic as a supernova. Betelgeuse had not exploded. Instead, it had coughed out a titanic cloud of superheated gas. As this material cooled, it condensed into an immense veil of stardust, a cosmic smokescreen that temporarily blocked a vast portion of the star's light from our view. This was not an ending, but a fascinating symptom of the star's violent, unstable old age. The great dimming provided a front-row seat to the final, messy chapters of a massive star's life. We witnessed in real time the processes that precede a supernova, the convulsive ejections of a star shedding its own skin. It transformed Betelgeuse from a static point of light into a dynamic, living character in a cosmic drama. This event did more than advance science. It created a profound personal connection for millions. It made the life cycle of stars feel immediate and tangible. We were not reading about stellar evolution in a textbook. We were watching it unfold, and it forces a sobering reflection. Betelgeuse is over 600 light-years away, a safe distance for its eventual explosion. But what if a closer star, one of the dozens within 100 light-years, were to follow the same path? A nearby supernova would be more than a light show. It would bathe our planet in radiation, potentially triggering mass extinctions and rewriting the very chemistry of our atmosphere. The dimming of a single star reminded us that the universe is not a static backdrop, but an active, powerful, and occasionally dangerous participant in our story. This tangible connection to stellar death brings a new urgency to our search for other living worlds and raises a chilling question about the universe we inhabit. Is it a quiet neighborhood or a dangerous one where such cosmic violence is common? A simple, repetitive beep became the sound of a new era. On October 4, 1957, that signal broadcast from the heavens was not a natural phenomenon, but a human-made object, Sputnik 1, tracing a path across the sky. To the scientists who built it, it was a triumph of engineering, a polished metal sphere no larger than a beach ball. But to the political and military leaders of the West, that steady chirp was a declaration of war from orbit. The Soviet Union had not just launched a satellite, it had demonstrated a terrifying capability. The very rocket that placed Sputnik in space could just as easily deliver a nuclear warhead anywhere on the globe, rendering oceans and alliances obsolete. Overnight, the United States felt vulnerable, its technological superiority shattered. This was the Sputnik crisis, a seismic event that fused the Cold War with the cosmos. The response was swift and total. Panic transformed into purpose. Within a year, the United States established the National Aeronautics and Space Administration, consolidating its civilian space efforts under a single banner. Congress passed the National Defense Education Act, pouring billions of dollars into science, mathematics, and engineering programs, a desperate attempt to catch up and create a new generation of rocket scientists. The space race was no longer a metaphor. It was a real high-stakes competition for ideological supremacy, where every lunar probe and every manned mission was a propaganda victory. The launch of that small, beeping sphere did more than start a political race. It fundamentally altered humanity's relationship with the universe. We were no longer earthbound observers gazing up at the stars. We had become active participants, a species that could now touch the void. This shift from passive watching to active engagement marked our true birth as a spacefaring civilization. The competitive fervor of this national effort, however, would eventually give way to a moment of profound global unity, where the whole world held its breath for a single, shared goal. The vast gray desolation of the lunar surface stretched out below Apollo 8, a barren and alien landscape of craters and dust. Then, something unexpected and profoundly beautiful happened. As their spacecraft swung around from the far side of the moon, the astronauts saw it, a sight no human eyes had ever witnessed before. Earth, our home, was rising over the stark, lifeless horizon. It was a vibrant swirl of blue and white, a perfect, delicate marble suspended in the infinite blackness of space. In that single, breathtaking moment, the crew understood. They were not just explorers visiting another world. They were inhabitants of a tiny, isolated oasis, the only place they had ever known, seen now from the outside for the very first time. Bill Anders quickly snapped a photograph, an image that would become one of the most influential in human history, Earthrise. This was not just a picture of a planet. It was a mirror held up to all of humanity. The photograph made abstract ideas terrifyingly concrete. There were no lines dividing nations, no flags, no signs of human conflict or engineering. There was only a fragile-looking sphere of life, wrapped in a thin, shimmering atmosphere that seemed as delicate as a soap bubble. That atmosphere, that single layer of gas, was all that protected everything we know and love from the lethal vacuum of space. The image arrived at a crucial time, as the modern environmental movement was just finding its voice. Earthrise gave that movement its most powerful symbol, a visceral reminder that we all share one finite and vulnerable biosphere. It triggered a profound shift in human consciousness, fostering a sense of global citizenship. For the first time, we could see with our own eyes that our divisions are human inventions, and our common destiny is tied to the health of that single, beautiful world. This new perspective from the outside forced us to look back inward, to truly value the complex atmospheric events that make our existence possible. What cosmic phenomena, for instance, create the very air we breathe and the magnetic shield that guards us from the sun's fury? Our planet's own atmosphere became the site of a shocking cosmic discovery. High above the frozen expanse of Antarctica, scientists detected a void, a tear in the very fabric of our planetary shield. In 1985, researchers from the British Antarctic Survey announced they had found a catastrophic thinning in the ozone layer, a protective blanket of gas that absorbs the sun's most harmful ultraviolet radiation. The data was undeniable. A hole had opened in the sky, and it was expanding at an alarming rate. The cause was traced directly to human activity, specifically to a family of seemingly miraculous chemicals called chlorofluorocarbons, or CFCs. These compounds were everywhere, in refrigerators, air conditioners, and aerosol spray cans, praised for their stability and safety. But that stability was the problem. Once released, they drifted intact high into the stratosphere, where the sun's powerful ultraviolet rays broke them apart, releasing chlorine atoms that acted as a catalyst, relentlessly destroying ozone molecules. A single chlorine atom could annihilate thousands of ozone molecules before finally settling down. This was not a local issue. It was a planetary-scale crisis, revealing with brutal clarity that humanity had acquired the power to inadvertently damage its own life support system. The discovery triggered a global wake-up call. For the first time, a direct, observable threat from human technology demanded an immediate international response. The result was the Montreal Protocol of 1987, a landmark treaty that unified the world in a common cause. Nations agreed to phase out the production of CFCs, a monumental task that required retooling entire industries and finding new, safer alternatives. It worked. The treaty stands as one of the most successful examples of global environmental cooperation in history. The ozone hole is now slowly, steadily healing, a testament to our ability to diagnose a problem and act collectively to solve it. This success story, born from an atmospheric observation, provides a crucial blueprint for the future. It proves that when faced with undeniable evidence, humanity can unite to mend the very sky above us, a vital lesson in cooperation for the next great planetary challenge we now confront. A global network of telescopes pointed simultaneously toward a single point of light 55 million light-years away. On April 10, 2019, the world saw the result, a fiery ring of orange and yellow encircling a perfect circle of shadow. This was the supermassive black hole at the heart of galaxy Messier 87, and humanity was looking directly at its event horizon for the very first time. The achievement was the work of the Event Horizon Telescope, a collaboration so vast it effectively turned our entire planet into a single, giant radio dish. 8 observatories across the globe, from the high deserts of Chile to the volcanic peaks of Hawaii, synchronized their observations with atomic clocks. They gathered so much data it was easier to fly physical hard drives to a central processing facility than to send the information over the internet. For 2 years, supercomputers worked to piece together the fragments of this cosmic signal, assembling the final, iconic image that confirmed a century-old prediction. The dark shadow at the center was not the black hole itself, for a black hole emits no light. It was the black hole's gravitational shadow, a region where spacetime is so warped that light cannot escape, silhouetted against the incandescent glow of superheated gas swirling at nearly the speed of light. This was the ultimate proof of Einstein's general theory of relativity in its most extreme environment. The image transformed these cosmic monsters from mathematical curiosities and science fiction tropes into tangible, physical objects. We could now see the engine that powers distant quasars and governs the evolution of entire galaxies. This monumental feat of international cooperation showed that by working together, humanity could accomplish the seemingly impossible, photographing a cosmic phantom 6.5 billion times more massive than our Sun. The successful imaging of such a distant, profound mystery underscores the importance of another, more practical form of cosmic observation. While we learn to see the invisible in the deep cosmos, we must also keep a watchful eye on the nearby space where our own survival is at stake. The year 2004 began with a celestial alarm bell. Astronomers at the Kitt Peak National Observatory in Arizona spotted a new asteroid, and its preliminary orbit sent a shockwave through the global scientific community. Designated 99942 Apophis, named for the Egyptian god of chaos, this 300-meter-wide chunk of rock was put on a trajectory that gave it a 2.7% chance of striking our planet on Friday, April 13, 2029. For a brief, tense period, this was the highest probability ever assigned to a potentially hazardous object. The numbers were stark. An impact would release energy equivalent to over 1,200 megatons of TNT, enough to devastate an entire region and trigger a global catastrophe. The world held its breath as headline after headline proclaimed the doomsday rock. This was not a distant, theoretical threat from a science fiction film. It was a real object with a name and a date, a tangible danger hurtling through the void directly toward us. The initial scare, however, was short-lived. As more tracking data poured in from observatories around the world, astronomers refined their calculations. They discovered that a key, previously unobserved close approach in 2021 would act as a gravitational keyhole, subtly altering its path. When that data was incorporated, the risk for 2029 was completely eliminated. The collective sigh of relief was audible, but the lesson was indelible. Apophis had served as a global fire drill, a stark demonstration of our vulnerability and the critical need for precise, continuous observation. This near miss galvanized the international astronomical community like never before. Funding and focus poured into programs dedicated to cataloging near-Earth objects. The mission was clear: find them before they find us. This new urgency directly fueled the development of active planetary defense strategies. It proved the necessity of missions like NAS, a double asteroid redirection test, or DART, which would later successfully demonstrate the ability to alter an asteroid's path by crashing a spacecraft into it. Apophis became the poster child for a threat we could now actively manage, transforming cosmic anxiety into a catalyst for human ingenuity. We learned that our survival might one day depend not on fleeing a threat, but on having the foresight to give it a gentle, calculated nudge. This monumental shift from passive observation to active defense mirrors another profound change in our relationship with the cosmos, one where we look to the sky not for dangers to avoid, but for the resources that could build our future among the stars. A rocket slammed into the moon at 5,000 miles per hour, and its impact was a deliberate success. In 2009, NASA L-Cross mission sent an empty Centaur rocket stage on a collision course with the permanently shadowed floor of the Cabeus crater near the lunar South Pole. The following spacecraft flew straight through the resulting plume of ejected material, analyzing its composition in the minutes before it too crashed into the surface. The data sent back was unequivocal. The plume contained significant amounts of water ice, a discovery that fundamentally rewrote our understanding of the moon. We had long thought of our celestial companion as a bone-dry desert, but here, hidden in eternal shadows where temperatures never rise above -400 degrees Fahrenheit, were vast reservoirs of frozen water. This was not just a scientific curiosity, it was the key to unlocking the solar system. Water is the oil of space exploration. It is not merely for drinking or growing food. With the application of electricity, a process called electrolysis, it can be split into its core components, hydrogen and oxygen, the very same propellants that power the vast majority of modern rockets. This transforms the moon from a barren destination into a cosmic gas station and a waypoint. The economic implications are staggering. Launching anything from Earth's deep gravity well is astronomically expensive. But launching from the moon with its much weaker gravity and a ready-made supply of fuel could slash the cost of deep space missions by orders of magnitude. A lunar base is no longer just a symbolic outpost, it is a practical stepping stone. It becomes a hub where spacecraft can refuel, resupply, and then journey onward to Mars and the asteroid belts, all powered by resources mined from the lunar soil itself. This discovery of water ice has fundamentally altered the roadmap for every space agency on Earth, shifting our focus from mere visitation to sustainable presence. It encourages us to look past the moon to the ultimate cosmic question. If the building blocks of life and survival are so common, how many other worlds might hold the final, most precious ingredient, life itself? A volunteer named Jerry Amon was scanning reams of data from the Big Ear radio telescope in Ohio when a string of code leapt from the page. It was August 15, 1977. The characters, 6 letters and numbers, represented a signal so powerful and so strange that Amon circled it in red pen and wrote a single, breathless word beside it. Wow! For 72 seconds, a narrowband radio burst, precisely tuned to the frequency of hydrogen, the most common element in the universe, had slammed into the receiver. It came from the direction of the constellation Sagittarius, and it bore all the hallmarks of an artificial broadcast, a signal that nature, as far as we know, does not make. Then, just as suddenly as it appeared, it vanished. decades of follow-up observations using ever more sensitive equipment have heard nothing from that same patch of sky. The WOW signal remains a perfect singular mystery, a cosmic shout in the dark that was never repeated. Its very nature makes it the most compelling and frustrating candidate for a potential alien message in the history of the search for extraterrestrial intelligence. It is not proof, but it is a profound possibility, a ghost in the machine that perfectly embodies the emotional core of our quest. Are we alone? The WOW signal is the universe offering a whisper that maybe, just maybe, we are not. This one unverified event has since fueled countless scientific papers, inspired new listening campaigns, and deepened the philosophical debate about our place in the cosmos. To hear such a signal, even once, is to confront the staggering implication that another mind from another world might be reaching out. The search continues, not for that one signal, but for the next one, driven by the hope that the WOW signal was not an anomaly, but a herald. This enduring human drive to find answers in the cosmic silence brings us to the final event on our list, a new eye on the universe that promises to transform not just what we see, but how we see everything. A million miles from Earth, a delicate and terrifying mechanical ballet unfolded in the absolute silence of space. The James Webb Space Telescope, a technological origami of gold-coated mirrors and sunshield the size of a tennis court, had to perform a series of hundreds of critical deployments without a single error. One snagged cable, one stuck latch, and the $10 billion observatory would become the most expensive piece of space junk in history. For weeks, the world watched and held its breath as each nerve-wracking step was confirmed, from the unfurling of its colossal sunshield to the precise alignment of its 18 hexagonal mirror segments. Success was not guaranteed, but failure was not an option. Against all odds, it worked. This was not just another telescope launch. It was the opening of a new eye on the cosmos, an instrument so powerful it was built to be a time machine. By collecting the faint, stretched light from the farthest reaches of the universe, the James Webb can peer back over 13.5 billion years to an era when the first stars and galaxies were igniting from the primordial darkness. Its early images have already upended our understanding of cosmic dawn. We expected to find small, infant galaxies slowly merging into larger ones, but Webb revealed fully formed, massive galaxies much earlier than any model predicted. It is as if we opened a history textbook to the first chapter and found a sophisticated civilization already thriving, forcing a complete rewrite of our theories on how structure emerged in the young universe. Beyond these ancient lights, Webb has another revolutionary mission: to sniff the air of distant worlds. By analyzing the starlight that filters through an exoplanet's atmosphere during a transit, its spectrographs can detect the chemical fingerprints of water vapor, methane, and carbon dioxide. The ultimate goal is to find a telltale mix of gases, a potential biosignature that might hint at biological activity. We are no longer just counting planets. We are beginning to study their weather and chemistry from a mind-boggling distance. The James Webb Space Telescope is more than a scientific instrument. It is a promise. It is the culmination of decades of human ingenuity and unprecedented international cooperation, a gift from our generation to the future. Perched at its lonely gravitational outpost, it ensures that the cosmic story, the very narrative of how astronomical events rewrite human history, is poised for its most thrilling chapters yet. This journey through 28 cosmic encounters reveals a single, transformative truth. The ancient wall that separated the heavens from the earth has completely dissolved. We began as terrified spectators, interpreting eclipses as divine judgments and comets as omens of doom, our fate seemingly written in the stars by indifferent gods. But over millennia, our role has dramatically changed. We have become active participants in a cosmic dialogue. We now predict planetary motions with breathtaking accuracy. We use the moon's gravity to slingshot probes into the outer solar system, and we mine asteroids for the raw materials to build our future. The story of our species is not one of isolation on a pale blue dot, but a continuous collaboration with the universe. This cosmic partnership touches every facet of our existence. Our very biology is built from stardust, the heavy elements forged in supernova explosions. Our cultures were shaped by the stars, from the calendars that dictated planting seasons to the celestial stories that defined our gods. Our technology, from the first navigational sextants to the global positioning satellites that guide us today, is a direct response to the challenges and opportunities presented by the cosmos. We are not just living on a planet, we are living within a dynamic solar system, a vibrant galaxy, and an expanding universe that actively participates in our story. Recognizing this profound interconnection is our most vital responsibility. It is the key to navigating a future filled with both incredible promise and existential risk. The same cosmic environment that delivered the water for our oceans also sends asteroids hurtling toward us. The same starlight that inspires poets can, from a nearby supernova, sterilize entire worlds. Our survival and our flourishing now depend on this hard-won cosmic perspective, on seeing ourselves not as masters of the universe, but as its conscious partners, tasked with the stewardship of our fragile world as we reach for the stars. This intellectual journey from astrology to astrophysics charts a fundamental shift in human consciousness. We began by looking at the heavens and seeing a screen for our own dramas, a place where gods wrote messages of warning or favor. Every eclipse was a divine judgment, every comet a herald of a king's fall or a dynasty's rise. The sky was a text to be interpreted, not a physical system to be understood. It was a world ruled by meaning, where celestial events held direct, often terrifying, consequences for human affairs. This was the realm of astrology, where the stars were thought to exert a direct influence on our lives. But slowly, painstakingly, a new way of thinking took root. It started with the meticulous record-keeping of priests and the first inklings of pattern, the realization that the sun and moon moved in cycles that could be predicted. The ability to forecast an eclipse was the first great crack in the astrological worldview, proving that these awe-inspiring events were not arbitrary acts of God, but products of a predictable clockwork. This was the birth of astronomy as a predictive science, a transition from asking what the stars mean to asking where they will be. The ultimate triumph of this new approach came with the discovery of Neptune, a planet found not by gazing with wonder, but by calculating with mathematics. The universe was no longer a mystical realm, it was a solvable equation. This set the stage for the final, breathtaking leap into modern astrophysics. We stopped being mere mapmakers of the solar system and became cosmic archaeologists. We now use the immutable laws of physics, tested in laboratories on Earth, to decode the light from quasars billions of light years away, to understand the nuclear furnaces inside stars, and to trace the history of the universe back to its first fiery moments. This evolution is the story of humanity growing up, of replacing a fearful relationship with the cosmos with one of profound curiosity and intellectual power. Our quest is no longer for omens but for origins, driven by the conviction that the universe is not only knowable, but is waiting to tell us its story. Our history with the cosmos compels us to look forward, to navigate a future that is both perilous and filled with infinite promise. The threats are real and demand a unified response. A future asteroid impact is not a matter of if, but when. and our survival may one day hinge on the planetary defense systems we build today, like the DART mission, which proved we can nudge a celestial target. This is not a task for one nation alone. It requires the kind of global cooperation that healed the ozone hole, a shared commitment to protecting our only home. Yet the same cosmic environment that sends asteroids our way also offers the keys to our expansion. The water ice confirmed on the Moon is not merely a scientific fact, it is the foundation for a new era of exploration, a potential off-world gas station that could fuel our journey to Mars and beyond. The thousands of exoplanets we have discovered tell us that the galaxy is teeming with real estate, other worlds that could one day become waypoints or even new homes for humanity. These opportunities point toward an inevitable interplanetary future, transforming us from a single planet species into a cosmic civilization. And then there are the fundamental discoveries that reshape our very souls. Knowing the universe had a beginning in the Big Bang and that it is fueled by dark energy forces us to confront our place in this grand narrative. Are we a fleeting accident, or are we the universe becoming conscious of itself? The search for meaning is now intertwined with the search for exoplanet atmospheres and the echoes of the cosmic microwave background. The legacy of these 28 events is a clear mandate. Our future will be written in the language of gravity and starlight, requiring vigilance against cosmic dangers, relentless curiosity to seize celestial opportunities, and a collaborative spirit that transcends earthly borders. The next great chapter of human history will not be confined to this pale blue dot. It will be authored amongst the stars. From the supernova that shattered ancient philosophy to the telescope now gazing at the dawn of time, these 28 celestial encounters reveal a profound partnership. The cosmos has never been a mere backdrop. It has been an active, silent collaborator in the human epic, toppling empires with a single eclipse, birthing new sciences from stardust, and humbling us with the sheer scale of our cosmic insignificance, while simultaneously revealing the precious rarity of our pale blue dot. Our own story is in its deepest essence a chapter in the universe's grand biography. As Carl Sagan so beautifully reflected, we are a way for the cosmos to know itself. This journey through the stars is an invitation to transform your own gaze. The next time you stand under the night sky, see it not as a passive canvas of distant lights, but as the other half of a dynamic, ongoing conversation. The next event that rewrites our history, that alters our understanding of reality, could be discovered tomorrow, its light already racing toward us. If this exploration of our cosmic past has captivated you, ensure you do not miss the next chapter by subscribing, and share your thoughts on which event most astonished you in the comments.